The morning of December 16, 1944, near the Belgian town of Malmedy, a column of American engineers stood before a gorge that had no bridge. The Amblev River, swollen with winter rain, cut a dark channel 40 feet below where the roadbed ended abruptly in shattered concrete and twisted steel. German demolition teams had done their work well. What remained of the original stone arch bridge lay in fragments at the bottom of the ravine, testimony to the Wehrmacht's scorched earth retreat through the Ardennes forest. Lieutenant Colonel David Pergrin, commanding officer of the 291st Engineer Combat Battalion, walked to the edge and looked down. His battalion had been pushing forward with the First Army's advance, repairing roads, clearing mines, and rebuilding infrastructure as fast as the infantry could take ground. Now, with Patton's Third Army racing toward the German border and supply lines stretched to breaking, this destroyed crossing represented more than an engineering problem. It was a choke point that could stall an entire offensive. Behind Pergrin, 6x6 trucks idled in a line that stretched back half a mile. Each carried ammunition, fuel, rations, and winter clothing for forward units that were already running dangerously low. The December cold had come early and hard that year. Men were fighting in inadequate gear, and every hour of delay meant more frostbite casualties, more immobilized tanks with frozen fuel lines, more artillery batteries rationing shells. "How long?" asked the major from division headquarters who had driven up to assess the situation. Pergrin studied the gap. In peacetime, with proper equipment and unlimited time, a permanent bridge across this span would take months. The standard military solution, a pontoon bridge, was impossible here. The current was too fast, the banks too steep, and besides, pontoons couldn't support the weight of Sherman tanks and heavy trucks that needed to cross. A timber trestle bridge might work, but that would require weeks of cutting lumber, pouring foundations, and assembling the framework. Weeks they didn't have. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 48 hours, Pergrin said. Maybe 72 if we hit bedrock when we dig the abutments. The major shook his head. You've got 24, maybe less. Intelligence says the Germans are massing armor in the Eifel. If they counterattack and we can't resupply forward units, we'll lose everything we've gained in the past month. Pergrin didn't argue. He'd seen the same intelligence reports. What he didn't say was that he had no idea how to span this gorge in 24 hours with the equipment his battalion possessed. The engineering manuals didn't cover this scenario. The standard bridge-building procedures he'd learned at Fort Belvoir assumed time, materials, and working conditions that bore no resemblance to a muddy Belgian forest in winter, with the German army potentially regrouping for a major offensive. But in the back of one of his trucks, covered with a tarpaulin and largely forgotten in the chaos of the advance, sat 26 panels of steel. Each panel measured 10 feet long by 5 feet high and weighed 270 pounds. They were components of something called a Bailey Bridge, a design so new that most American engineers had never seen one assembled, let alone built one under combat conditions. The British had delivered these panels 6 weeks earlier, with minimal instructions and the assurance that the system was quite straightforward, really. Pergrin had attended exactly one demonstration of the Bailey system at a rear area depot in September. He'd watched British engineers bolt the panels together like an oversized erector set, and he'd thought at the time that it looked suspiciously simple. Too simple. Nothing in war was ever as easy as it appeared in controlled demonstrations. But now, standing at the edge of this gorge with an impossible deadline and no other options, he found himself thinking about those steel panels. The question wasn't whether the Bailey Bridge could work. The question was whether it could work here, now, with untested crews and a clock that was already ticking toward disaster. To understand why Pergrin's situation seemed impossible, one must first understand the state of military bridge engineering in December of 1944. For centuries, armies had struggled with the fundamental problem of crossing rivers and gorges. Alexander the Great's engineers built pontoon bridges across the Hellespont. Roman legions carried prefabricated timber components for temporary spans. Napoleon's Corps of Engineers pioneered mobile bridging equipment that could be assembled under fire. But the essential challenge remained unchanged: how to span water obstacles quickly enough to maintain operational momentum. By the Second World War, the problem had become exponentially more difficult. Modern armies moved on wheels and tracks, not feet and hooves. A division in 1944 required hundreds of vehicles: tanks weighing 30 tons or more, tank destroyers, self-propelled artillery, supply trucks carrying everything from ammunition to blood plasma. Any bridge had to support not just the weight of marching infantry, but the sustained traffic of mechanized warfare. The United States Army had 3 standard solutions for river crossings, and all 3 had severe limitations. Pontoon bridges, the most common option, consisted of inflatable or metal floats that supported a roadway of wooden planks. Engineers could assemble them relatively quickly, often in 6 to 12 hours, and they worked well on calm, slow-moving rivers. But pontoons had critical weaknesses. They couldn't handle strong currents or steep banks. They required constant maintenance as the floats shifted and the planking wore out. Most importantly, they had strict weight limits. A standard pontoon bridge could support light vehicles and infantry, but heavy tanks had to cross one at a time at reduced speed, creating bottlenecks that could last for hours. Fixed bridges, the second option, meant building a permanent or semi-permanent structure from timber or steel. These could handle any weight, but construction time was measured in weeks or months. Combat engineers learned to build timber trestle bridges, driving pilings into riverbeds and constructing frameworks of heavy beams. The work was skilled, labor-intensive, and vulnerable to enemy artillery. A single, well-placed shell could collapse sections that had taken days to build. In fluid combat situations where front lines shifted daily, investing weeks in a fixed bridge was often impractical. The third option was simply to ford the river if conditions allowed. Engineers would scout for shallow crossings, improve the approaches with gravel, and send vehicles through the water. This worked only for small streams and imposed its own delays as each vehicle negotiated the crossing individually. Deeper rivers, or those with soft bottoms, were impassable. None of these solutions addressed the scenario Pergrin faced at Malmedy. The Amblev Gorge was too deep and fast-flowing for pontoons, too wide and urgent for a timber bridge, and obviously impossible to ford. The destroyed permanent bridge had taken Belgian engineers months to construct in peacetime. Rebuilding it under winter conditions with limited materials and hostile forces potentially approaching was simply not feasible in any time frame that mattered operationally. This wasn't just an engineering challenge. It was a microcosm of a larger problem facing the Allied advance across Europe in late 1944. The armies had moved so fast after breaking out of Normandy that they'd outrun their supply infrastructure. The port of Antwerp wouldn't open until late November. Everything, from gasoline to ammunition to replacement troops, had to be trucked forward from the Normandy beaches, a distance of more than 400 miles. Every destroyed bridge meant another delay, another choke point, another opportunity for the overstretched supply system to fail completely. The doctrine of the time held that rapid exploitation of breakthroughs required engineers to keep pace with advancing armor. But keeping pace meant solving bridge problems faster than doctrine suggested was possible. Engineers needed a system that combined the speed of pontoons with the strength of fixed bridges, something that could be assembled quickly by troops without specialized training, something that could span significant distances and support heavy loads. The military establishments of Europe and America had been searching for such a system since the First World War. Dozens of designs had been proposed, tested, and found wanting. Each prototype seemed to sacrifice either speed or strength or both. The solution to this seemingly intractable problem had been invented by a man who was neither a soldier nor, initially, particularly interested in military applications. Donald Coleman Bailey was born in Rotherham, Yorkshire, in 1891, the son of a clerk. He studied civil engineering at Sheffield University, graduating in 1913, just in time to watch the profession he'd chosen be conscripted into the industrial slaughter of the First World War. Bailey served as a junior officer in the Royal Engineers, experiencing firsthand the frustration of trying to move armies across landscapes where every bridge had been destroyed. After the war, Bailey joined the British Civil Service, working for the War Office's experimental bridging establishment at Christchurch, Hampshire. It was quiet work, far removed from the headlines, involving endless calculations and tests of bridge designs that rarely saw practical use. Bailey was methodical, precise, and uninterested in self-promotion. Colleagues remembered him as a man who brought his lunch in a tin box every day, worked through problems with the patience of someone solving chess puzzles, and rarely spoke unless he had something definitive to contribute. In the late 1930s, as Europe began rearming and the possibility of another war loomed, Bailey began thinking about the bridge problem with fresh perspective. He'd seen the limitations of existing military bridges. He'd studied the captured German equipment from the First World War, noting that even Germany's vaunted engineering corps struggled with the same challenges. What was needed, Bailey concluded, wasn't a clever variation on existing designs. What was needed was a completely different approach. The conceptual breakthrough Bailey achieved was both simple and radical. Instead of designing a bridge as a unified structure that had to be transported and assembled as a whole, what if the bridge consisted of identical panels that could be carried by hand and bolted together in virtually unlimited configurations? Each panel would be small enough for 6 men to lift, simple enough that no special tools or skills were required for assembly, and strong enough that multiple panels could be joined to create spans of varying lengths and load capacities. Bailey sketched his first designs in 1936. The panels measured 10 feet wide by 5 feet high, fabricated from steel plate formed into a lattice pattern. Each panel weighed roughly 270 pounds, light enough for a small team to maneuver, but heavy enough to provide structural rigidity. The genius lay in how the panels connected. Vertical pins dropped through holes at each corner, joining panels side by side to create the length of the bridge. Horizontal braces connected panels vertically to create additional strength. The entire system relied on simple mechanical principles. The panels formed trusses, distributing load through compression and tension along the lattice structure. When Bailey presented his design to the experimental bridging establishment in 1937, the response was skeptical. Senior engineers argued that such a simple system couldn't possibly achieve the necessary strength-to-weight ratio. The mathematics, they insisted, didn't support the claimed load capacity. Bailey quietly went back to his calculations, refined his stress analysis, and returned with proof that the design worked. Still, institutional inertia and budget constraints meant the project moved slowly. A prototype wasn't built until 1941, after the war had already begun and the need for better bridging equipment had become desperately apparent. The first full-scale test took place in November of 1941 at Christchurch. A Bailey Bridge span of 70 feet was assembled by a team of Royal Engineers who had never seen the components before. They worked from written instructions alone, with no specialized equipment beyond standard hand tools. The bridge was completed in 90 minutes. When tested with a 30-ton tank, the structure held without deflection beyond calculated tolerances. The simplicity that had caused skepticism turned out to be the design's greatest strength. There were no complex joints to align, no precision machining required in the field, no need for cranes or heavy lifting equipment. 6 men with wrenches could build a bridge strong enough to carry an army. Even then, adoption was slow. The British Army's initial order in early 1942 was modest, only enough panels for experimental use in North Africa. But as those first Bailey bridges proved themselves under combat conditions, orders increased exponentially. By 1943, British factories were producing thousands of panels monthly. The American Army, initially committed to its own bridging systems, began requesting Bailey components after observing their performance in Sicily and Italy. By late 1944, Bailey bridges had become standard issue for engineer units throughout the Allied armies. Lieutenant Colonel Pergrin ordered his trucks unloaded at 1400 hours on December 16, 1944. The Bailey Bridge components came out piece by piece, 26 main panels, each a rigid lattice of welded steel, measuring precisely 10 feet long by 5 feet high. There were also crossbeams called transoms, wooden decking planks, steel pins the diameter of a man's thumb, and connection plates that would join everything together. The entire kit, when assembled, would create a single-span bridge, 70 feet long, just enough to reach across the Amblev Gorge with minimal clearance on either side. Pergrin gathered his section leaders and spread the British instruction manual across the hood of a jeep. The manual was thin, barely 20 pages, with simple diagrams showing how panels connected. There were no complex calculations, no lengthy procedures, just straightforward assembly steps that looked, frankly, too simple to work. Staff Sergeant Curtis Halt, who had helped build timber trestle bridges in Louisiana during training, studied the diagrams with open skepticism. "Sir, this looks like something you'd build with a toy construction set," Holt said. "How's it supposed to hold 30 tons? Pergrin didn't have a good answer. The manual provided load ratings, specifications that claimed a single-story Bailey could support 40 tons if properly assembled, but the numbers seemed to contradict everything the engineers had learned about bridge construction. Steel trusses required careful calculation of stress points, precise alignment of members, and rigid connection systems that took skilled welders to fabricate. Yet here was a design that relied on simple pins dropped through holes, with panels bolted together by hand. The cognitive dissonance was profound, but Pergrin had attended that demonstration in September, and he'd seen British engineers assemble a bridge span in less than 2 hours. The structure had held a Churchill tank, which weighed nearly 40 tons fully loaded. Either the British had discovered something revolutionary, or there was a fatal flaw that hadn't yet revealed itself under combat conditions. With no other options available, Pergrin chose to trust the design. "We're going to follow the manual exactly as written," he told his section leaders. "No modifications, no improvements. The British have tested this under combat conditions. We're going to replicate their procedure." The first challenge was preparing the banks. The original stone bridge had rested on abutments that were now partially destroyed. The Bailey system required level launching surfaces on both sides of the gap, areas where the bridge could be assembled horizontally and then pushed out over the void. Pergrin's men set to work with picks and shovels, clearing debris and grading the earth. A bulldozer scraped and leveled the approach on the near bank, creating a platform 30 feet deep. On the far bank, engineers rappelled down with tools and cleared a similar space, working under the constant awareness that German observation posts might be watching from the hills. By 1600 hours, as winter darkness began to fall, the approaches were ready. Portable floodlights, powered by generators, turned the construction site into an island of harsh white light surrounded by forest blackness. The temperature had dropped to well below freezing. Men's breath came in clouds. Metal surfaces were cold enough to freeze skin on contact. Pergrin ordered the first panel moved into position. 6 men lifted each panel, 3 on each side, gripping the steel framework at designated carrying points. The panels were awkward, not extraordinarily heavy for 6 men, but bulky and difficult to balance. They maneuvered the first panel onto the launching platform and set it down, with the lattice side vertical, exactly as the manual specified. A second panel was brought up and positioned adjacent to the first. 4 steel pins, each 18 inches long, dropped through aligned holes at the corners where the panels met. The pins fell into place with solid metallic clicks. Connection plates were bolted across the joint. The process took 8 minutes. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. A third panel joined the first 2, then a fourth. The bridge began to take shape, growing horizontally along the launching platform like a steel spine. The lattice structure, when viewed from the side, formed a series of triangles and rectangles that distributed stress through the framework. Each panel added rigidity to the whole. What had seemed flimsy when individual panels were lifted became increasingly solid as the structure lengthened. Transoms, the crossbeams that would support the roadway decking, were bolted between the vertical panels at 6-foot intervals. These too were simple components, steel beams with connection brackets that hooked over the panel framework and bolted into place. No welding, no precision alignment, just bolts tightened with standard wrenches. The wooden decking planks, each 12 feet long and 10 inches wide, were laid across the transoms and secured with metal cleats. By 2200 hours, the bridge structure had reached 30 feet in length, extending from the launching platform toward the gap. The men worked in shifts, some assembling panels, while others prepared components for the next section. The rhythm of construction settled into a routine: lift, position, pin, bolt, move to the next panel. Pergrin walked alongside the growing structure, checking each connection personally. The pins had to drop completely through the holes, sitting flush at the bottom. The bolts had to be tightened too. Specifications, not finger-tight but torqued with full body weight on the wrench handles. The critical moment came at 0300 hours on December 17th. The bridge structure now measured 70 feet long, assembled completely on the near bank and ready to be pushed across the gorge. This was the procedure that seemed most impossible to the engineers watching. The entire bridge would be shoved forward on steel rollers, cantilevered out over empty space, until the far end reached the opposite bank and dropped onto the prepared abutment. Pergrin ordered winches set up on the far side of the gap. Steel cables were stretched across the gorge, running from the winches back to the nose of the bridge. A team of engineers had crossed the river earlier by rappelling down one side and climbing up the other, work done in darkness over a 40-foot drop with the sound of fast water echoing up from below. Those men now operated the winches, ready to pull as the bridge was pushed. On the near bank, 30 men positioned themselves along the sides of the bridge structure. They would push in coordinated shoves, moving the entire assembly forward on roller units that the British called launching rollers. These were simple steel cylinders, mounted in brackets that attached to the bottom chord of the bridge. As the structure moved forward, rollers at the rear would be picked up and carried to the front, leapfrogging along to maintain continuous support. On my count, Pergrin called out, 1, 2, 3, push. The men heaved against the steel framework. For a moment, nothing happened. The bridge seemed immovably fixed to the launching platform. Then, with a grinding screech of metal on metal, it shifted forward 6 inches. The roller brackets had bitten into the framework, and the bridge was moving. Again, push. Another heave. Another 6 inches. The rhythm established itself. Push, reposition, push again. The bridge crept forward at an agonizing pace. When the nose reached the edge of the bank and projected out over the gorge, several engineers stepped back instinctively. The physics seemed wrong. 70 feet of steel bridge, weighing approximately 15,000 pounds, was being held up by nothing but its own structural integrity, cantilevered into space. The lattice panels that had seemed so simple during assembly now demonstrated their engineering sophistication. The top chord of the bridge, the upper horizontal member of the truss, was in compression, being squeezed by the weight trying to bend the structure downward. The bottom chord was in tension, being stretched by the same forces. The diagonal and vertical members of the lattice transferred these forces throughout the structure, distributing the load so that no single component bore excessive stress. Donald Bailey's calculations, worked out on paper in a quiet office in Hampshire, were being proven in real time over a Belgian gorge. As more of the bridge extended over the gap, the deflection became visible. The unsupported end drooped slightly, sagging under its own weight exactly as Bailey's stress calculations had predicted. The manual specified maximum allowable deflection. For a 70-foot span, the nose could drop up to 18 inches before structural limits were exceeded. Pergrin watched the deflection with measuring instruments borrowed from a surveying kit. 12 inches, 15 inches, 16 inches. The bridge was performing within tolerances. At 0430 hours, the nose of the bridge reached the far bank. Men on the opposite side grabbed the steel framework and guided it onto the prepared abutment. The moment the far end made contact with solid ground, the deflection disappeared. The bridge straightened, supported now at both ends, transforming from a cantilever into a simple span. The entire push across the gap had taken 90 minutes. What remained was finishing work. Additional panels were added at each end to create approaches that ramped up to road level. Safety railings fabricated from steel cables were strung along both sides. The wooden decking was inspected and any loose planks resecured. Engineers tested each connection point one final time, checking that pins were fully seated and bolts properly tightened. At 0600 hours, barely 16 hours after Pergrin had received his orders, the bridge was complete. A single-lane span 70 feet long, 5 feet wide at the roadway, standing 35 feet above the river. It looked impossibly delicate, more like a temporary scaffolding than a military bridge. The steel lattice was exposed on both sides, offering no visual mass or solidity. It seemed to be nothing but air and angles held together by pins. Pergrin ordered a proof test. A 6x6 truck loaded with 5 tons of engineering equipment was driven onto the bridge at walking speed. The structure flexed slightly under the load, a movement of perhaps 2 inches at the center span, well within design parameters. The truck crossed without incident. A second truck followed, then a third. Each crossing demonstrated the bridge's capacity. At 0700 hours, a Sherman tank approached. This was the real test. The M4A3 Sherman weighed 33 tons, fully loaded with fuel and ammunition. If the bridge could support this, it could handle anything in the American inventory. The tank commander was ordered to cross at minimum speed, 5 miles per hour, with instructions to stop immediately if any structural distress became apparent. The tank's treads clanked onto the wooden decking. The bridge sagged visibly under the weight, deflecting at the center by nearly 6 inches. Men watching from the banks held their breath. Steel creaked under stress, but the deflection stabilized. The pins held. The connections remained solid. The tank continued across, its weight causing the bridge to flex rhythmically as it moved, but never exceeding the calculated load, capacity. When the Sherman reached the far bank and drove off onto solid ground, a spontaneous cheer went up from the engineers. The Bailey Bridge at Malmedy remained in continuous use for the next 4 months. Between December 17, 1944, and April 20, 1945, more than 12,000 vehicles crossed that span. The daily traffic included Sherman tanks, M10 tank destroyers weighing 32 tons, M12 self-propelled guns weighing 37 tons, and countless supply trucks carrying everything from ammunition to gasoline to medical supplies. Not a single structural failure occurred. The bridge required minimal maintenance, wooden decking planks replaced as they wore, bolts retightened weekly as vibration loosened them, but no modifications to the steel structure itself. This single bridge, assembled in 16 hours by combat engineers who had never built one before, eliminated a choke point that could have paralyzed an entire army's advance. The mathematics of military logistics made this clear. A division in 1944 required approximately 600 tons of supplies daily to maintain combat effectiveness. This included fuel for vehicles, ammunition for weapons, rations for personnel, and replacement equipment for items worn out or destroyed. Without the Malmedy Bridge, supplies for forward units would have required a detour of 40 miles over secondary roads, adding at least 3 hours to each round trip. The cumulative delay would have reduced supply deliveries by approximately 30%, enough to seriously degrade combat capability. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Pergrin's success at Malmedy was not unique. Across the European theatre, in late 1944 and early 1945, Bailey bridges became the standard solution for river crossings and destroyed infrastructure. The numbers documented their impact with stark clarity. Between D-Day in June of 1944 and VE Day in May of 1945, Allied engineers erected more than 4,000 Bailey bridges in northwest Europe alone. These spans ranged from simple single-story bridges like Malmedy's to massive multi-story structures that crossed major rivers. The most dramatic example came at the Rhine crossing in March of 1945. The Ludendorff Bridge at Remagen, captured intact by American forces on March 7th, collapsed on March 17th after sustaining damage from German artillery and deliberate sabotage attempts. The collapse killed 28 American engineers who were working on repairs. With the only intact bridge across the Rhine gone, the Allied advance threatened to stall. Engineers responded by building Bailey bridges at multiple crossing points. At Remagen itself, a Bailey span measuring 978 feet was completed in under 8 days, spanning the Rhine with a structure that could support 40-ton loads moving continuously in both directions. The speed of Bailey Bridge construction compared to traditional methods revealed the revolutionary nature of the design. Historical data from earlier wars provided benchmarks. During the First World War, British engineers building a timber trestle bridge across a 100-foot gap required an average of 14 days with a full company of engineers. In the American Civil War, Union engineers under Herman Haupt achieved remarkable speed with prefabricated bridge components, but still needed 3 to 4 days for similar spans. The Bailey system reduced these timeframes by an order of magnitude. A trained crew could erect a 100-foot Bailey span in 12 hours. With multiple crews working simultaneously on longer spans, construction rates approached 100 feet per day. The logistical implications were equally significant. A complete Bailey bridge kit for a 100-foot span weighed approximately 12 tons and could be transported on 3 standard military trucks. No special equipment was required for assembly. No cranes, no pile drivers, no welding apparatus. Everything needed came in the kit: panels, pins, transoms, decking, and connection hardware. This meant that bridge building capability could be distributed throughout an army. Every engineer battalion could carry enough Bailey components to create multiple spans, eliminating the need for centralized bridge building units that had to be requested and scheduled. The structural efficiency of the Bailey design also allowed for adaptability that previous systems lacked. By stacking panels vertically, engineers could create double-story or triple-story bridges with exponentially greater load capacity. A single-story Bailey span supported 40 tons. A double-story configuration, using the same basic panels simply stacked too high and reinforced with additional bracing, could support 70 tons. Triple-story bridges reached 100 tons of capacity, sufficient for the heaviest equipment the Army possessed. This modularity meant that a single inventory of standardized components could meet virtually any bridging requirement. Field modifications extended the system's utility even further. Engineers learned to build Bailey bridges with curved alignments by introducing slight angles between panels. They created floating Bailey bridges by mounting the structure on pontoons, combining the strength of fixed spans with the adaptability of floating bridges. They used Bailey panels as temporary roofing for damaged buildings, as structural supports for collapsed tunnels, and as frameworks for improvised docks and piers. The design's simplicity made it a universal building material, limited only by the engineer's imagination. By war's end, the statistical record documented Bailey's achievement. More than £700 million of Bailey components were manufactured during the war years. Production facilities in Britain, the United States, Canada, and Australia produced panels at rates exceeding 10,000 per month by 1945. The bridges built with these components carried millions of tons of supplies and equipment, transported entire armies across rivers that would otherwise have stopped their advance, and demonstrated conclusively that the impossible bridge, imagined by a quiet civil servant in Hampshire, had become one of the war's most important tactical innovations. Donald Bailey never sought fame for his invention, and the nature of military secrecy during wartime ensured he didn't receive it until long after the bridges bearing his name had changed the course of the war. Throughout 1943 and 1944, while thousands of Bailey bridges were being erected across North Africa, Italy, and France, Bailey himself remained at the experimental bridging establishment in Christchurch, working on refinements and training engineers in the system's use. He was a civil servant, doing his job, drawing a modest salary, and living in the same unremarkable house he'd occupied since before the war. The recognition, when it came, was characteristically understated. In 1946, Bailey was appointed an Officer of the Order of the British Empire for his contribution to the war effort. The citation mentioned innovative bridge design without elaborating on the scale of impact. Those who knew the full story, the engineers who had built the bridges under fire, the logistics officers who had watched supplies flow across spans, erected in hours rather than weeks, understood what the brief citation represented. Field Marshal Bernard Montgomery, never generous with praise, called the Bailey Bridge the best thing in the war from an engineering perspective. General Dwight Eisenhower stated that Bailey's design had been worth its weight in gold, perhaps the only military metaphor adequate to describe its value. Bailey himself deflected such praise. In the few interviews he gave after the war, he emphasized that the bridge was simply an application of basic engineering principles, nothing revolutionary, merely competent design work. This humility was genuine, not false modesty. Bailey had approached bridge building as a problem requiring solution, and he'd solved it with the methodical patience that characterized all his work. That the solution proved so universally applicable, so adaptable to conditions he'd never personally witnessed, was perhaps evidence of truly fundamental insight rather than narrow cleverness. The immediate post-war period saw Bailey Bridge's transition from military expedient to permanent infrastructure. Across Europe and Asia, spans erected as temporary wartime measures remained in place for years, sometimes decades. The bridges were simply too useful to replace. Civilian engineers, surveying the bomb-damaged landscape of 1945 and 1946, found themselves ordering Bailey components to restore transportation networks. The panels that had carried Sherman tanks across the Rhine now carried commercial trucks across rivers in France, Belgium, and Holland. In some cases, these temporary bridges became permanent through sheer inertia. The Bailey span at Nijmegen in the Netherlands, erected during Operation Market Garden in September of 1944, remained in continuous use until 1969, 25 years after its construction. During that quarter-century, it carried millions of vehicles, weathered countless storms, and required only routine maintenance. When finally replaced by a modern concrete structure, the Bailey panels were carefully disassembled and transported to other locations where they continued service. The design's longevity surprised even Bailey, who had calculated the system for temporary military use, not multi-decade civilian operation. Lieutenant Colonel David Pergrin, whose successful assembly of the Malmedy Bridge demonstrated the Bailey system's practicality under combat conditions, continued his military career after the war. He retired as a colonel in 1963, having served in Korea and various engineering assignments. In his memoir, published decades later, Pergrin devoted an entire chapter to that December night in 1944, describing it as the moment when theoretical engineering became undeniable reality. The bridge he'd built in 16 hours, despite his initial skepticism, had convinced him that some innovations were so fundamentally sound that they transcended the usual problems of field implementation. The broader engineering community gradually recognized Bailey's achievement as the war receded into history. The Institution of Civil Engineers, Britain's most prestigious engineering society, awarded Bailey the Telford Gold Medal in 1948, acknowledging that his bridge design represented a significant advance in structural engineering. Universities began teaching the Bailey system as a case study in elegant problem-solving, demonstrating how complex challenges could be addressed through simplification rather than elaboration. The bridge appeared in textbooks not as historical curiosity, but as functional example of good design principles. To understand the Bailey Bridge's true impact on the Second World War requires examining the mathematics of military logistics with some precision. Modern warfare in the 1940s consumed material at rates that would have been incomprehensible to commanders from earlier eras. A single American armored division, the standard combined arms formation of the period, included approximately 11,000 personnel and required between 500 and 700 tons of supplies daily to maintain combat effectiveness. This figure included fuel for nearly 400 tanks and tracked vehicles, ammunition for weapons ranging from pistols to 155mm howitzers, rations for all personnel, medical supplies, replacement equipment, and maintenance materials. These supplies arrived at the front via truck convoy, typically traveling distances of 100 to 300 miles from depot to combat unit. The efficiency of this supply line determined operational capability. A breakdown anywhere in the chain, a destroyed bridge forcing detours, a congested road causing delays, reduced the flow of material and directly degraded combat power. The correlation was not abstract but mathematical and immediate. An armoured division short of fuel could not advance. An infantry division short of ammunition could not attack. artillery batteries rationing shells lost their effectiveness as suppressive fire. The Bailey Bridge's contribution lay in its elimination of bridge-related choke points. Before Bailey's design became standard, river crossings represented predictable delays. Engineers needed days or weeks to span significant obstacles, during which advancing units had to pause, allowing enemy forces to regroup and prepare defenses. The operational tempo of modern warfare, the ability to maintain continuous pressure on a retreating enemy, depended on maintaining momentum. Every delay allowed the enemy breathing space, and that space could be measured in lives lost during subsequent battles that would have been unnecessary if the advance had continued uninterrupted. Statistical analysis conducted by the U.S. Army's Operations Research Office after the war attempted to quantify this impact. The studies examined campaign timelines, correlating bridge construction times with advance rates and casualty figures. While acknowledging the difficulties of isolating single variables in the chaos of combat, the researchers concluded that Bailey bridges reduced river crossing delays by an average of 60 to 70% compared to previous methods. This translated to faster operational tempo, shorter campaigns, and measurably lower casualty rates as enemy forces had less time to establish defensive positions. One particularly striking example came from the Italian campaign. The Allied advance up the Italian peninsula from September 1943 through May 1945 crossed countless rivers flowing west from the Apennine Mountains. German forces, fighting a skilled defensive campaign, demolished bridges systematically as they retreated. Allied engineers responded by erecting Bailey bridges at nearly every crossing. By war's end, more than 3,000 Bailey spans had been built in Italy alone, creating an artificial transportation network that replaced the demolished permanent infrastructure. The German army, observing the speed with which Allied engineers restored crossing capability, attempted to develop its own equivalent system. The Kastenträger Bridge, designed in 1944, borrowed concepts from Bailey's design but suffered from typical German over-engineering. The panels were heavier, requiring 8 men instead of 6 for handling. The connection system was more complex, requiring specialized tools and more time for assembly. Production problems meant that few complete bridge sets ever reached combat units. By the time German engineers had a working alternative, the war's outcome was no longer in doubt. Soviet forces, advancing from the east, initially used primarily pontoon bridges supplemented by timber trestle construction. However, after Lend-Lease deliveries began including Bailey Bridge components in late 1943, Soviet engineering units adopted the system enthusiastically. The simplicity appealed to Soviet doctrine, which emphasized standardization and ease of field maintenance. By 1945, Soviet engineers were erecting Bailey bridges across rivers in Eastern Europe and Germany, often using captured German labor for assembly work. The same design served armies with vastly different military cultures and operational doctrines, testament to its fundamental soundness. The Pacific Theater presented different challenges but similar solutions: jungle environments, heavy monsoon rains, and rivers that could rise 10 feet overnight required bridging systems that could be assembled quickly and modified as conditions changed. Bailey bridges proved adaptable. Engineers in Burma built spans during the dry season, then raised them on improvised pilings when monsoons came. In the Philippines, Bailey components replaced destroyed bridges on Route 3, the main supply line for American forces advancing toward Manila. The bridge's modularity allowed engineers to adjust span lengths and load capacities to match local conditions without requiring different components or specialized training. Donald Bailey died in May of 1985, at the age of 93, having lived to see his bridge design become one of the most widely used engineering solutions in history. By that time, Bailey bridges had been erected on every continent, in climates ranging from Arctic tundra to tropical rainforest, crossing obstacles from narrow creeks to major rivers. The design had been licensed to dozens of countries, modified and improved by successive generations of engineers, but remaining fundamentally true to Bailey's original conception. Simple panels, pinned connections, modular assembly. The endurance of the design into the late 20th century and beyond reflected qualities that transcended its wartime origins. Bailey had created not just a bridge for a specific conflict, but a system that addressed universal engineering challenges. The need to span obstacles quickly, with minimal equipment and maximum reliability, existed in peacetime as much as in war. Natural disasters, infrastructure failures, remote construction projects, all presented scenarios where Bailey's principles remained applicable. Modern military engineers continue to carry Bailey-derived bridge systems, now fabricated from aluminum alloys or composite materials, but retaining the essential logic of panelized construction and pinned connections. The bridges themselves, the physical steel structures erected between 1941 and 1945, largely disappeared as peace allowed replacement with permanent infrastructure, but scattered examples survived as historical monuments. A Bailey span preserved at the Imperial War Museum in London allowed visitors to walk across the steel lattice and examine the connection details. In Normandy, a Bailey bridge erected during the breakout from the beachhead in June of 1944 remained in place, maintained by local authorities as a reminder of the campaign. These relics conveyed, more effectively than any description, the audacious simplicity of Bailey's design. The theoretical impact extended into engineering education. Bailey's approach to the bridge problem, reducing a complex challenge to its essential elements and then solving those elements with maximum simplicity, became a case study taught in design courses. The bridge illustrated principles that applied far beyond structural engineering: the value of standardization, the power of modularity, the importance of field-level usability. Students learned to ask Bailey's fundamental question: what is the simplest solution that meets all requirements? This question, applied rigorously, often revealed possibilities that more elaborate approaches obscured. Lieutenant Colonel Pergrin, standing at the edge of that gorge in December of 1944, had faced an impossible problem with no time and no good options. The Bailey Bridge had not made the problem easy. Building a span in 16 hours under winter conditions while potentially under enemy observation remained extraordinarily difficult. But it had made the problem solvable. That distinction, between impossible and merely very hard, defined the bridge's true contribution. War presented countless scenarios where the impossible had to be attempted anyway. Having tools that shifted those scenarios from impossible to achievable, even if barely so, changed outcomes. The final accounting of Bailey's contribution resisted simple quantification. How does one measure the value of bridges that allowed supplies to reach armies that would otherwise have stalled? How does one calculate the worth of operational tempo maintained, of enemy forces kept off balance, of campaigns concluded months earlier than they might have been? The mathematics existed but remained approximate, estimates rather than certainties. What could be stated with certainty was that Donald Bailey, a quiet civil servant who had approached bridge design as a problem requiring solution, had created something that fundamentally changed how armies moved and operated. In the end, the story of the Bailey Bridge returned to that December morning at Malmedy, the gorge that had seemed an insurmountable obstacle, the engineer who had no idea how to solve it, the stack of steel panels that looked too simple to work. And then, 16 hours later, the bridge standing where no bridge should have been possible, carrying tanks and trucks and the material weight of an army's ambition. That transformation from impossible to achieved, repeated thousands of times across dozens of countries, represented Donald Bailey's legacy. Not just a bridge, but proof that the right idea, executed with enough care and simplicity, could change what was possible. The war had demanded solutions to problems that peacetime engineering had never confronted. Bailey had provided one of those solutions, perhaps the most elegant and universally applicable. His bridge, born from necessity and refined through methodical calculation, had helped carry the Allies to victory. And when peace came, the bridges remained, spanning rivers and time, connecting then to now, reminding anyone who cared to notice that sometimes the impossible becomes routine, and the routine changes everything. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.